All right, let's begin. Today we'd like to discuss the construction of, mainly the construction of the other four graphs of the other four trig functions that we haven't mentioned recently. Thank you guys for your attention over there. So it'll be very helpful having spent a lot of time with sine and cosine. I think we're very, I'm going to hope after that warm-up too, you've shown that you're really good at doing transformations of all kinds with those two functions. That'll provide a really excellent foundation as we do these. Now I'm already aware that some of you have actually constructed these graphs before, and there's a little bit of a mixed background in this room as far as how much experience one of you has versus the other. If you had AAF last year, my impression is that you have at least constructed the basic graphs of these functions. I'm going to push you to think a little more deeply about them today in ways maybe you haven't thought thoroughly about. And I'd also like to push you to do some transformations of these too, and the homework will have you do some of those too. Though at this point in your mathematical life, that shouldn't scare you at all. Like if I show you a brand new function you've never seen before, like right now, you should be able to do transformations of that function approximately like 2 seconds later, right? Because you know how to do transformations of every function, don't you? Don't you have that understanding? That won't actually be the big focus of today, even though I do expect that you can do transformations of these functions. We'll do an example or two, but and the homework will have those for you. So let's start with this, and I'll make this a little discussion around your table. I'd like you to come up. You can make it a competition if you like. But be in brainstorm mode here. I'd like you to come up with the longest list you can. In a minute, we're going to actually construct the graph of cosecant, the function cosecant x. Now, I don't want you to just rush to a graph of that, even though I know some of you already have a little bit of an awareness of what the graph of cosecant does look like. What I'd like to start with is the observation that cosecant is 1 over sine. Maybe you've thought about that before. Along with the graph in front of us of sine, which you don't maybe need in front of you, you have it in your head maybe, I don't know. And I would just like you to create as long a list with your table as you possibly can of properties that you think might be like connections you can make between the graphs. So be in brainstorm mode. I'd like you to not just think of like, well, if I plug in this and then I do 1 over that, then I get this. Like go deeper. Like think about function behaviors here. Think about your list from unit 1. Like, what can you say globally about these things and the connections between them? Come up with a list of connections between the graphs. Come up with a long list. Write it down.
Whenever it's like, oh, and I'm like, It's like 0.0.
Some of you are more focused than others on generating.
No, it can't equal.
Give me another 60 seconds here. Again, I want to push you. Think about asymptotic behavior. Think about increasing, decreasing behavior. Think about symmetry. Think about continuity. Everything you know. Everything's on the table.
Oh, wait. No, the
Main range, everything. I want to understand that.
Yeah, y can equal pi. Y can
That's not 5.
That's, no.
Oh, you mean
Oh, for the y value.
Yeah. Every single asymptote.
Yeah, every pi value. That's what you mean.
Yeah, but there are asymptotes assigned next to it.
Those are the asymptotes, though.
Write down one more thing, maybe.
No, like you said, taking 0, but y is
Yeah, no, we're mixing. You guys are
Okay, ladies, gentlemen, let's begin. Okay, so I'm going to come to a table here. I'd like to hear an observation. I'd like to come to another table. You'll give a different observation. This requires that you listen one to the other. Make sure that you aren't repeating things that have already been said. Make sure you were additive in our discussion. So, how about we start with you guys over here? Who all of you brought Cheetos for each other today? That was awesome. The table unity over there is really strong.
Not like actual asymptotes.
Thank you, Katie.
As with 0, pi, 2 pi, negative 2 pi, etc. Because that's when sine is equal to 0, and it would be like 1 over 0 pi.
And yeah, plus or minus all those things. Because you said sine of 0 is 0, for example. So that means.
So when you flip it over, it'd be like 1 over 0, and that's undefined. So
Okay, and 1 over cosecant of 0 is then like 1 over 0, which is undefined. Now I'm going to push you in the same way that I pushed this group back here. We're having a good discussion about this. And I'll leave this, I don't need you to answer this necessarily, but I do want you to think hard about this question. Is it necessarily true that if a function is undefined, then it must have a vertical asymptote at that location? So I need you to, like, in order to justify why this means that there's a vertical asymptote, I maybe need you to say more, but I don't know. I hear you though, and you are right that there are vertical asymptotes on this graph, but I just want to push you on a little bit on what you think of as the definition of a vertical asymptote. It isn't simply where a function is undefined. So think about that. And you're welcome to add to that if you like as we go here. But great, we have some vertical asymptotes in the graph. That's interesting. Give us something else. How about you guys? Give us another thing you notice.
Because cosecant of x is equal to 1 over sine of x, and the numerator, 1, is never going to equal 0, because it's 1. The graph of cosecant of x is not going to have any x.
All right, so no x-intercepts. For cosecant. I didn't want to write down everything you said, but it was all great. Okay. But okay, so how about you guys over here? What kind of is another thing on the list? Anything you came up with? Inverses. What does that mean? I just need a refresher on what the word inverse means. Does anyone want to fight them on that?
What?
The claim on the table is that these are inverses.
No, I'm always ready to say no.
Yeah.
Y values and y equals cosecant acts as reciprocals of the y values.
I like the word reciprocal, but I'm not a huge fan of the word inverse. Can you tell me why I don't like the word inverse? Inverse has a proper technical mathematical meaning. And this isn't necessarily it. Do you remember what we mean by inverses? Like, what do we claim if we claim that f and g are inverses, two functions f and g? And I'm not sure that's happening here. Do you agree? So inverse is maybe not a great word, but we will write down that they're reciprocals. And that's not just about the two functions, right? That's also about every value, right? Every value is the reciprocal. If we get one value on the sine curve, we just take its reciprocal to get the cosecant value. That's cool. Maria, did you have something else to add there, or did we kind of cover it? Or sorry, Piper. Who had your hand up back there? Someone? Okay. Here we go. Okay. How about you guys up front? Come on, another property that's not on our list. Or no? The answer can be no.
I think, yeah, I think what we thought it was.
Okay. Maybe I should go into like volunteer mode. Anyone have any table have an idea that wasn't yet mentioned? Huh? It's not a function?
Wait, no, yeah, it is.
Oh, that's I might fight you on that too. I mean, we take this outside. Okay.
No, it's a function over and over because, like, technically speaking, it never repeats, like, in the black.
Okay. Wait, slow down. You saying it is a function? Yeah, I think it is a function. I mean, just the way we've defined it means that it must be a function here too. Yeah. Yeah? How do you know that? I have never seen a picture of it though. It's easy to show that a function isn't one-to-one by just simply providing, but just providing one example and an example of one type. You'll come up with one, right? Can you do that for me? Show me why it's not one-to-one by coming up with an example. We'll come back to you, Grant. But I agree. But I agree, it isn't one-to-one. Grant's going to come up with an example where that shows that that's not true. Lauren, you have another thought? Oh, interesting observation. Does that seem to be true, people? That the local, and you use the word local. Why? All right, and local, I think, did you say both? Local bins become local maxes too? Is that what you said? That's an interesting observation. Do you understand my notation? I'm just trying to be quick in writing it. Yeah. Oh yeah, no one has said anything about that. Go ahead.
Since when sine of x as it approaches the values where x.
Let's say 0,
where
for
y
example.
equals 0,
Let's say 0, for example.
So as sine of x approaches that, it's gonna get like the absolute value of it is getting smaller. So when you have 1 over something that's continually getting smaller, then it's gonna trend towards either upwards or downwards, depending if it's positive or negative. But it's never gonna hit it. So
But never hit it. Yeah. So what happens if you plug in? Yeah. Let's actually think about plugging in a number like 0.001. What is the sign of 0.001 approximately? It's approximately the same, isn't it? It's approximately 0.001, isn't it? Is that fair? You think about the fact that We're just looking basically for the arc length. Remember that the sine function, we know the arc length, the radian measure of the arc length is 0.001. If we're talking about 0.0018 radians. And that's a really small arc length. I'm talking about the unit circle now. You with me on this? So the arc length that cuts off, that angle cuts off, is 0.001 in measure, isn't it? Well, isn't that approximately the same as the vertical segment that represents sine? So the sine function and the arc length there, the radian measure, like x equals sine x, doesn't it? For really small values of x. Just like, kind of, that's not the same when it's small. But anyway, sine of 0.0001 is approximately 0.0001. And then we want to think, what's 1 over that? I don't know what 1 over 0 is. I just don't know that. But I do know what 1 over 0.0001 is. It's what? Yeah, it's whatever. I don't know how many zeros I said. It's 10,000 or something, isn't it? Good. So now I'm feeling, don't you feel it? Don't you feel the asymptote? Doesn't that feel asymptotic? You want to get closer to a big number? Put in a number closer to 0, yes? Is that not, now that's an asymptote. I want to make sure you're not just, now that's an asymptote, right? And we're not sure whether that's plus or minus infinity, right? It depends on how we're approaching 0. But I want to make sure you go back to the definition of a vertical asymptote from like unit 1. And that was it. It was like a limit definition, wasn't it? Use this language of approaching. Thank you so much, Bryn. Appreciate that. Bringing that to the table. The arrows, that makes all the difference. Okay. Yeah, thank you. Thank you. Grant, how are you doing on your counter exam?
At x equals pi over 2 and 5 pi over 2, y equals 1.
All right. Does that demonstrate why this isn't 1-to-1? You just found. Explain why that demonstrates that this is not 1-to-1.
Because one y value corresponds to 2 x values, and that doesn't make it 1-to-1.
Yeah. And how does that connect to the graph of sine? Is sine 1-to-1?
No.
No. Does that imply maybe that 1 over sine isn't 1-to-1 too? Like maybe we can make an even more general claim. That in general in life, if we come across a function f that's not 1-to-1, is it necessarily true that 1 over f is also not 1-to-1? Prove it, right? I think you could prove that, maybe in general. So there's a connection there too. Because sine isn't 1-to-1, maybe that implies cosecant must not be 1-to-1 either. Right? Think about it. Anything else not on this list? Anybody? We do need to cut this off in a minute. You're just being silent back there, Rick? You had like a beautiful observation that no one has said. Odd. Do you see it? Do you agree? And again, maybe you can make a general statement about f and 1 over f and their symmetry. Just about any two functions that are reciprocals of one another in their symmetry. But anyway, yeah, cosecant and sine are both odd. Maybe we'll make another observation in a minute here. There are other observations. No one said anything about increasing or decreasing behavior. No, I don't know. Domain and range. No one mentioned anything about those things. So, all right, let's go ahead and graph it here real quick. The discussion previous to this suggests that maybe we want to think about the sine graph on here. So I'm just going to produce that real quick. And I think you guys, some of you have done this before, so I don't want this to be like a chore necessarily. But the thought process we just had, I think, is really good. And we won't go through that again with the other graphs, but as long as we've had that kind of thought once, I think this is going to be very good for us. It's good, I think, to connect this back to graphs we know a lot about, like sine. We've gotten used to sine. We're really good at sine. I'm going to make this, just for the sake of for fun, let's make this 2. Thank you. Appreciate it. And I'm going to graph sine really carefully here. Here we go. Boom, boom, boom. Well, no, everything settled down. We're good at this is one we know and love, right?
That's too fast and too quick. I got a head.
I didn't mean that. I meant 1. All right, so there's sine. We just need it for reference. Now we're going to graph actually cosecant. Remember, that's what our thought process is here. We're thinking like, oh yeah, this is 1 over sine. So we're going to have that close at hand. We're going to be thinking about it. Even if we don't graph it, you're probably thinking about it. Okay, so now let's graph cosecant on top. I don't think anyone said this either. What's the value at 1? At x equals 5 or 2? Excuse me.
1.
Okay, yeah, right.
Good one.
And similarly, at every other place where sine will equal 1, cosecant will agree. No one said that. But there it is. Similarly, good, yeah. Right. We'll have agreement on the values there as well. And then we'll use the observation that Laura first brought to us, and that's that there are these vertical asymptotes every time sine is 0. And we made that a little more rigorous, talking about why that's really happening when we get vertical asymptotes in life.
In life.
Great. So, I mean, we are in a good situation now to actually already kind of graph this a little bit. I do want to make maybe one more observation, and that's that, like, as sine increases, what is cosecant doing?
Decreases.
Yeah, and in general, is that a rule? Go through each interval and see. Is that always happening?
Yeah.
Anytime sine is decreasing, is it also true that cosecant is increasing?
Yeah.
No one said that? I thought I'd throw that out there. Okay. And by the way, what do we have? We could actually plug in some nice values, because you're like trig people. You're good at. What's the cosecant of pi over 3, for example? Cosecant of pi over 3. Or how about pi over, actually no, nicer would be like pi over 6, wouldn't it? That would be 2. Yeah, let's do that. I'm not about messy values. All right. Pi over 6 would give us, and I don't know, is pi over 6 about there? I don't know, somewhere in there. You could be more precise than this. And pi over 6 will also similarly give us 2. And we get this asymptotic behavior that was claimed. We get this decreasing behavior that we just talked about. We get something like that, don't we? I honestly don't need very much detail on these graphs. As long as we the general behavior is close enough, whatever. There we go. And if you like afterward, you can get rid of the red graph. If you like that was just there, that's not actually that's not a feature of this graph. It's just there to help us think about it. Okay?
Wow.
Are you alright?
Technology.
Whoa. All right, so are you good with cosecant? Again, we spend lots of time on that. I'm just not even going to show you secant, right? Is that okay with you? There's just not an interesting discussion beyond what we've already had there. Tangent's worth like thinking through though, because it is actually interesting and different. Oh, sorry, one other observation that no one made. What's the period of this function cosecant? Yeah, again, think about the relationship between sine. The fact that the period of sine is 2 pi, like, necessitates that the period here will be 2 pi as well. Think about maybe why that's true. The period is 2 pi. That is, if you want to think about it in informal terms, it's the minimum distance you can copy and then paste repeatedly and get this picture. Yeah? Okay? All right, tangent. We're ready for tangent. So I don't want to have a protracted discussion. We're not doing any brainstorming on this, but let's just think, what are we thinking about that's going to guide us as we graph this? Yeah, again, we love sine and cosine, so maybe you don't need to. I mean, you know tangent pretty well too, because you're just getting good at these values. So if you don't want to think about this, that's also fine. But it is true that the fact that this is equal to sine over cosine, and you know those really, really well, might help. Okay, so that's good to have maybe by our side. So what's an observation you make that's really helpful right away as we're trying to graph this? Again, right now we're just trying to produce this graph, maybe. Yeah, Daniel, help us.
It would have the vertical axis.
Yeah, or we could be, yeah, exactly. When cosine is, but we can couch that in more asymptotic language, but yeah, certainly true. When cosine is 0, we will actually get asymptotes here. So when is cosine 0? Pi over 2, here's pi, here's 3 pi over 2. We want to be careful when saying multiples, because pi is a multiple, but it's not where cosine is 0. So we got to be careful with that a little bit. But I do agree that at pi over 2, and every odd multiple of pi over 2. We could say that. Every odd multiple of pi over 2, maybe, would be a way to say it. Okay. So 3 pi over 2. Tell me something else while I'm doing these. What else do you have for me? We still have not actually gotten a single point on the graph yet. I should have pre-done these graphs. Yeah, when sine is 0, we get tangent going to 0, right? Look at the fraction. So that happens at 0 and every integer multiple of pi, right? So at 0, tangent is 0. Again, you don't maybe don't even need to know. You just know that tangent of 0 is 0, and you might just know that tangent of pi is pi, right? And tangent of 2 pi, tangent of negative 2 pi. All these things, these are all 0. What's another nice value? I'm actually looking for a little on the hunt for some other nice values, maybe. Where does that happen?
I don't know how to say it. I just know that
You just happen to know what it looks like, but let's actually just generate some actual reasoning toward that. Yeah. Yeah, because I just happen to know that the tangent of pi over 4 is 1. Give me another value. Good, thanks. Thanks, Graham. What else you got? Another value? Maybe inside that first interval there. Negative pi over 4 seems to be giving us negative 1, 2. So I think, and we do have this asymptotic behavior, I think, as someone said. So I do think we get a picture like that, and for good reason, as we're plugging these in. And then we get some kind of repetitive behavior on these. What does the period of this function appear to be? Yeah, it appears to be actually not pi over 2. There's a snapshot of it. It keeps going, obviously. So yeah, it appears the period is what would you say? Actually just pi. It's interesting to me, and I have a lot more to say about that, but we'll just keep it there. So that's interesting to me, and it's also not just kind of like a cosmetic observation about this. When we go to graph, like, say, tangent of 2x, you'll need to keep that in mind. What's the period of tangent of 2x, for example? What does that represent in terms of transformations? Tangent of 2x. It's a horizontal shrink by a factor of a half or whatever. So the new period will be for that guy pi over 2. So just keep that in mind that this is something you'll always have to be thinking about as you're graphing tangent. Also cotangent too. All right, so let's actually try one of these here too. Let's actually do a graph where we have a little bit of transformation happening as well. We'll give this a try. I'll give you a minute or two, and I'll call someone up here to produce the graph for us in a second.
How many rounds are you freshmen on now?
Yeah, because the first game master was really bad. Oh, I was
And then you have to divide it by 2.
Okay, at least you guys are working. Oh my god.
They don't believe you. They believe that the government is trying to take away their game master. He knows that.
Are you done yet? Great.
I have it. So that the government can take away your line.
Oh, it's getting over there.
The regular sign, the regular period for sign is 2 pi, but this is tangent. The regular period is pi. Pi.
Oh, so whatever the period is, whether you got the computer is free.
Yes.
No,
Wait, so the period is 3 pi?
it's 3 pi. What she said.
And so
So what's that? Yeah, whatever.
it'd be like there.
Oh, yeah.
Oh, you're right.
So it still looks the same as the period. But it's
actually tastes like mouthwash.
Wait, no, you can use
Nah,
that.
it's more like
You can use that. Yeah, you can use that for taking. Add a bit of spice to it too. Right, so green and my green for you can do it. The Piper
For any function.
apparently Nyquil's will be. What color's Nyquil?
Oh, you've been sent
How
out.
am I supposed to use
I'm sorry.
I have to make
You make some progress on this?
That's Dayquil. Yeah.
Hit me up.
Hit me up with
Piper, please.
I'm actually so drugged down right now. Like, I'm
Come on, Piper, get me there too.
Emmanuel. Shame on you.
You know me already. You already know.
Wow,
Damn it, I wasn't.
Hey, that's cool. She only graphed one period, but I think that looks good.
The government can listen for a while.
Keep in mind, as I ask you to graph tangent and also cotangent graphs, I'm looking for maybe like 3 points on each branch, just to make it clear what. I would just love to make all the features of this graph obvious from the picture. So, like that -2 isn't obvious unless you do what Corinne did and like somehow indicate where that point went. You know? Yeah. Those 2 points.
Are we allowed, like, even if it's in data, can we do it in radians?
Yeah. Yeah, let's assume radians unless someone tells you otherwise there's degrees. IB will do what I did the other day where it has like a little degree mark there, something like that. They'll do that. So, yeah, any other questions about that one? Can you handle transformations? I feel like you can. By the way, no longer can we really call like 2 the amplitude. It's not a good name for it maybe, but it is, you can still call it the vertical stretch on the graph. There's a joke for you. I found this on the internet. There you go. You're welcome. Hilarious. It's hilarious. Yeah. Oh, I'm actually a little paranoid about government. On my this is my head.
I can't believe
This is my head. It doesn't belong to anybody else. I stole it from a friend.
that's amazing.
Leave that right there.
That's amazing.
Like a cat.
Oh my god.
I didn't know that. No, I didn't know that part about like Kira, you had that like, yeah. Try Cotangent if you will. What might help you in your thinking about this one?
1 over the other.
Well, you could do you could do 1 over tangent if you love tangent, or you can do cosine over sine. Whatever floats your boat.
I feel like that'd be weird. Sorry. Are you saying that? Or any of you a couple shots of that?
Really?
Yeah,
You
I
took that one.
I don't know.
Last. You're not saying until 6 o'clock.
5:30. We're leaving at 5:30.
Wait, did I say no? I said 5 minutes.
The hell, you said until 5:10.
Oh, is it 4:10 to 5:10?
Okay.
Oh, no. Sorry. No,
You scared me.
I'm getting confused with Wednesday. Wednesday is at 5:30. I can't. Today is it's less. I am so lost.
Nah, so be like all the way.
What is the cotangent?
-1.
I'm gonna say no.
In some respect.
Longest component for the
Cotangent.
What's the cotangent? Cotangent is 0.
Oh, now there's more absolute strikes.
There's not more. I don't think there's
Not more, just like.
Yeah, cosine of 0 is the cotangent of 0 is undefined.
Same thing with pi and
And okay, all right, I feel you. Okay. So pi and 2 pi. All right, and then what's going on? What else do you got for me? All right, what else you got for me? Let's come together on this one. Yeah, what do you got for me? Listen, shh. Thank you so much.
Pi over 2, comma 1, and negative pi over 2.
Okay, so we still have that pi over 2, like that agrees with the previous graph. At pi over 4, you mean? Or did you say, sorry. Negative pi over 2 and positive pi over 2. What do you get? Sorry, I interpreted what you said as what I thought I meant for you to say, but you didn't say it. So, what you were supposed to say. But pi over 2 is interesting to me. What do you get at pi over 2? I just did the pi over 4s. That's what I heard you say. They're 1 and negative 1. What's pi over 2 though? 0 and also negative pi over 2. I mean, there's no shame in plugging in a few points here, and you'll get these values. In fact, at these values, the tangent and the cotangent of pi over 4 are both, in both cases, 1, isn't it? They agree at that place. Like the graphs cross there, apparently. Anyway. You were thinking about pi over 4, weren't you? I see, I knew it. I was just reading your mind. Okay. Like I said, not too much to say about that one. All right, homework 5 tonight will be your joy. See you tomorrow.